Modern software handles real-time language translation, medical imaging, and code generation. This network of digital services operates as a constant layer of our daily infrastructure. These capabilities are the result of an 80-year effort to replicate the internal mechanics of biological intelligence. In 1943, neurophysiologist Warren McCulloch and mathematician Walter Pitts proposed that the activity of the human brain could be described through mathematical logic. They treated the individual neuron not as a biological mystery, but as a computational engine. Artificial intelligence did not begin with a silicon processor. Its first blueprint was a set of logical equations designed to mirror the firing of a nerve cell. In 1957, psychologist Frank Rosenblatt attempted to turn that mathematical blueprint into a physical machine. Working at the Cornell Aeronautical Laboratory, he built the Mark I Perceptron. The Perceptron was a room-sized assembly of tangled wires and rotary motors. Unlike modern software, this was a hardware image processor that used a grid of photocells to recognize basic shapes. The media response was immediate and speculative. The New York Times reported that the Navy expected these machines would eventually be able to talk, walk, and even become conscious of their own existence. But the machine had a specific mathematical limit. The Perceptron utilized a single-layer architecture, which meant it was incapable of solving nonlinear logic problems or recognizing complex objects in three-dimensional space. The gap between these publicized predictions and the actual mathematical constraints of the hardware caused interest in the field to stall. It set the stage for a total collapse in research funding. By the 1970s, the field entered the AI winter. Neural network research was largely abandoned by major institutions, and the biological model of computing became a scientific fringe. The problem was the lack of a learning mechanism. These early, simple networks were rigid. If the system made an error, there was no way for it to automatically adjust its own internal logic to improve. While the industry focused on traditional architectures that followed fixed, human-written instructions, a few researchers continued to focus on the biological model of connectionism. Artificial intelligence remained limited to basic pattern matching. Without a way to learn from errors, the technology could not advance toward solving complex, real-world problems. The breakthrough arrived in 1986. Geoffrey Hinton and his colleagues popularized a method that allowed multi-layer networks to finally learn from their own mistakes. This process is widely known as backpropagation. In a forward pass, data travels through the layers to produce a prediction. If it identifies an image incorrectly, the difference from the correct answer is the error. Backpropagation sends that error value backward through the network. It uses calculus to determine which connections contributed to the mistake, adjusting their mathematical weights. By repeating this loop, the network gradually minimizes its error until its predictions are accurate. This iterative learning process gave deep neural networks the autonomy to improve their performance without direct human reprogram. By the 2010s, deep learning could identify objects in photos, but language remained a bottleneck. Computers struggled to maintain the continuity of human speech. Earlier models processed text one word at a time in a sequence. By the time the network reached the end of a long sentence, it often lost the context provided by the first few words. This changed in 2017 with the introduction of the transformer architecture and a mechanism called self-attention. Self-attention allows a network to process every word in a sequence simultaneously. It assigns relevance scores to every word in a paragraph at once, enabling the system to understand how different parts of a text relate to one another. By providing a form of task-sensitive memory, self-attention unlocked the ability for models to generate and understand human-level language at scale. Today, we have moved from the 1943 chalkboard sketch to a global network of silicon-based intelligence. These systems learn through brute force optimization. They require millions of training examples and megawatts of power to iteratively adjust their mathematical weights. In contrast, the biological human brain learns from simple experiences and noisy data while consuming only 20 watts of power, roughly the energy needed to run a single light bulb. This gap in efficiency suggests that while our models are inspired by the brain, they operate on different functional principles. By pushing mathematical optimization to its limit, we have not replicated the human mind.